Good afternoon, everyone. First of all, on the periodicals, results were quite good compared to your senior batches. People have done really well, especially in the Viva. Few of you have done exceedingly well. That's good. Okay, and being after all, it's a new subject. You are, most of you are quite confident about your answers. Now, probably in a day or two, I'll just upload the key also, or maybe next week. So before the periodicals, we were talking about radars, general introduction to radars, and then finally we said that it has few problems like range ambiguity and Doppler ambiguity. Range ambiguity means you require a pulse repetition frequency which is very low, and if you talk about velocity ambiguity, you require a high PRF. So generally, if you talk about search radars, the PRF is around 1000 hertz, okay. And tracking radars will be around 8000 hertz. That's the sort of PRF you can expect. Now the third problem is, how do you distinguish stationary targets from moving targets? So if you are having a, like I told you last time, when an aircraft is flying very close to the hilltop, the reflection from the hill is going to be much greater than from the aircraft. So the aircraft echo gets masked. So how do we distinguish these? Differentiate the moving target from the stationary target. So that is the third challenge in the radar design. So this is your T is equal to 0. Okay. And as I told you earlier, it is time and range. It corresponds to the same thing in radar. So you have a hillock, and over that an aircraft is flying. Definitely what is seen by the radar controller is going to be a big patch. You will never be able to see the aircraft moving on that. So we'll have to do something to overcome this problem. Any suggestions? Open to the class, like how to overcome this problem. I want to differentiate between a moving target and a stationary target. Just from your high school physics.
Sir, we can send two signals, sir, and if there's a relative.
Two signals also, it's going to get, you're going to get the same reflection. So Sahana, anything from your side?
I think, sir.
You understood the problem, no? Like the reflection is coming both from the aircraft as well as the hillock. So the radar doesn't know where from it's coming. For that, it's just a signal. So on the radar screen, it's going to look like a huge patch.
Sir, can we use Doppler effect, sir?
Yes, good. Because any moving target, the reflected signal will have a plus minus shift of this frequency. Plus if it is approaching and minus if it is receding. What you learned in your high school, like a train going on a whistling and going on a platform, the frequency changes, though the actual frequency emitted by the horn is same, whereas what we hear, the frequency changes. So we'll have to use this function of Doppler effect or the phenomena of Doppler effect. Before going into a little bit of maths about it, we'll see how this system works. These radars are called moving target radars. It's called the moving target indicator, MTI radars, that's what they call it. And all radars nowadays are MTI radars. Okay. So let's start with the transmitter side. So let's say there is some local oscillator. It's called stable local oscillator, STALO. It's similar to what you have seen in your electronic communication module. It's basic transmitter. Okay. So this STALO is giving a frequency, let us say FL. It is mixed, we'll see why it is so, with another frequency FC. And totally the frequency which is going out is FL plus FC. Sum of two frequencies. I told you like mixer can give either difference or the sum of two incoming frequencies. Now this signal goes into a power amplifier because you require large power. Here if it is say 1 watt which is coming out, definitely here you are talking about 1 gigawatt. So that's the sort of amplification you require. And if you look at the modulator, it's a pulse modulator because all our waveforms in radar is pulsed. Okay, it's not a continuous wave. So you have to pulse modulate the signal and then amplify it, and then it goes out. So you have a target. Okay, so it goes and gets reflected back. So this is the basic transmitter chain. Okay. Now the reception side, you get the signal, reflected signal or the echo. Definitely it is some carrier plus minus FD. Since we have used FL plus FC, we will use the same term here. So the transmitted signal is reflected back, a portion of it, with a Doppler shift, okay, or phase shift. Frequency and phase, rate of change of frequency is phase. So there is either way you can interpret it. So there is a change. Depending on the velocity, now this Doppler is related to the velocity of the aircraft. And whether it's approaching or receding, that gives the sign of the shift. Now, so this duplexer we have seen, it basically is a switch between the transmitter and receiver to protect the receiver. Okay, so the signal comes here. Now you mix it with the stable local oscillator, STALO. So you can have a difference of these two things. So what you get is FC plus minus FD. You have an amplifier. Now this becomes the sort of intermediate frequency. If I remember right, I think we used to have some in radars. It is around 50 megahertz is the intermediate frequency. Just a standard. All radar devices they came out like a communication receiver. We have 10.7 megahertz and 455 kilohertz. Radars generally have this 50 megahertz components. Now there is one important thing which happens. There is something called as coherent oscillator. Okay. Now this serves as the base for the outgoing signal, and this is again fed into the into a block called phase detector, which is basically detecting the phase difference between the incoming signal and the outgoing and the coho. And this goes into something called as delay line cancel that I'll tell you later. Now we'll just see what is this phase detector because you're not come across this side term. Okay. Now let us say I'm showing you two different cases. One is a stationary target. So you transmit a pulse. Okay. It goes, strikes the target and comes back. Okay. But it can always come back with a phase change depending on the distance r. But what is going to happen is from with time, this particular phase change will be constant. What is coming out of a stationary target, the phase difference is going to be constant because the relative distance is same. But the moment you have a moving target, whether it's closing or receding, this phase becomes variable. So from with time, this phase difference between the coho and the incoming signal changes. And if we can feed this information into a box called phase detector, whose transfer function is something like this. So you have a phase difference between 0 to pi. And then for pi to minus pi, sorry, it's because the other way is also possible. It can be a receding target. So at 0 phase difference, it gives 0 volts. And at phase difference of pi, it gives some plus some volts. Similarly, if it is minus pi, it gives some minus volts. So the output can vary between this range minus V to plus V, depending on what phase we are getting. Phase difference is there between the incoming and outgoing signal. So this is a function of this box called phase detector. Oh, okay, now it's again I'm going to ask you this question. Like, okay, now I got a phase detector. How can I differentiate between a moving target and stationary target? Some scheme you can suggest by which we can differentiate these two targets. And the clue is this phase change, this phase of the incoming signal changes with time for a stationary target, for a moving target. It's not constant. Sanjay, did you understand the question?
Sir, can you rephrase the question, sir?
Yeah, okay. Now this whole box called as MTI is going to tell me about the phase change from the received signal. Now this phase change will be constant for a stationary target and variable for a moving target. Now I want to somehow, this information is coming to me in time, uh, because radar range is, let us say this is the scope, and range is complete thing, okay, say 0 to 100 kilometers. So I'm getting this information continuously. Let us say just one single pulse. I'm not even considering a radar which is rotating, just one single pulse transmitted, and I'm receiving at this portion. But what I'm receiving now is the phase information of the reflected signals. And to simplify the explanation, we'll just assume that the radar antenna is just pointing at one direction. Okay, slide, and then let's see whether you can explain. So I am showing you the outputs. Okay, try to make out the difference. Yeah, it's open to the class. Anyone can tell me how it's going to work. Again, x-axis is time. And you have the phase detector output in y-axis. Okay, I'll even try to make it simpler. This is pulse 1, then pulse 2, pulse 3, and pulse 4. No, what pulse 4? Pulse, yeah, 1, 2, 3. Even if we want to simplify it further, we can even delete this. Third pulse. Let's assume we are emitted 2 pulses, and we have a provision of recording it.
So what you gave us an explanation, sir. Can you tell the question?
See, this is the phase detector output for 2 consecutive pulses, which is recorded in time. And I have some medium of recording it. Now I want to find out from these 2 waveforms, where is the moving target? Because as I told you, stationary targets are also going to give you some output because there will be a phase difference. But that phase difference is constant.
Sir, the apparent increase in frequency.
No, the frequency information is lost. Now what you are getting is a voltage in time. Because indirectly it's there, but what is there visible to you is two signals for two consecutive pulses.
So they take the difference between those two pulses and where there's a drastic change.
Good, very good. So you subtract pulse 1 and pulse 2, and this goes as your output. Okay, so let us say we divide this into, it's called range bins. Okay, you divide this complete range into small bins. Bins is like dustbin. Okay, so whatever is the signal, these are analog in nature. So you can always digitize this and dump it into the respective bins. Let us say 1, 2, 3 and 100th bin. Okay, so that is for pulse 1. Now for pulse 2, again you will have another set of memory locations in the same order. So 1, 2, 3, so on and so forth for till the 100th bin. You dump all this data into the second location, memory location. Now all you have to do is just subtract these two bins, and then if it is not, it's a non-zero quantity, then it indicates that there is a stationary moving target. Of course, there will be some noise and all those things. You'll find some noise and all those stuff. That anyway, you can have a threshold. If the difference is greater than so and so limit, then you declare it as a moving target. So most of the books, they don't explain this properly. Even radar books, no, they students generally get confused. So it is actually phase detector output. One has to read carefully, then you will understand this particular thing. Is it okay, Solu? Are you getting it now?
Yes, sir. Sir, are those two pulses of same frequency and amplitude?
No, same pulse. What is going out of the transmitter is same. Okay, same amplitude, same frequency. There is no change. It's only the reflected signal which undergoes a phase change. Of course, amplitude is going to be very less compared to what has gone out. So this called as a delay line canceller because it delays by 1 PRF. So what you're going to do is you have this input coming in because it's analog in nature. You feed it into an ADC. One gets stored into a memory location called as a delay line, and the other one goes directly, and then you subtract these two signals. You'll get you'll get a waveform something like this. Okay, and then you're not worried whether it is positive or negative because all you know is there is a change. That's what is important. So you take the absolute value, and then this is going to be again up to this it's digital in nature, but displays require an analog. So you have a DAC over here. So finally you get it out for displaying the signal. So this is called as a delay line canceller. So just repeat it. This phase detector output comes here. It's analog in nature, so you have a ADC, dump the data into some memory location, for the first pulse, and the next pulse you dump it in another location, and bin wise you subtract these two information, then take the absolute value, which is again digital in nature, and then because analog displays require a analog signal, you have a DAC over here, and then display it on the PPI. Okay. So what appeared as a patch will now appear as a proper blip. In addition, you can use it for other data processing also, because anything which is digital gives you a lot of flexibility. So the whole thing can be sent into DSP, and DSPs can do a hell of a lot of things, much better than analog devices. So if you look at the block diagram, so you club all this receiver and phase detector into one box. So you have a delay line. Let's say it's V1 and this is V2, which is coming straight. Actually, this arrow is like this. Okay. So V1 minus V2 is any standard radar book will give you this derivation. Okay, V1 minus V2 is equal to sine times this into cos phi. Okay, now tell me what is the problem with this concept. And T is PR, 1 by PRF. Because this is delay in time, no? So you have to be careful about the units. The problem is here. If FD is equal to N by T, it can happen, right? FDs can take any value, depending on the velocity of the aircraft. So if it is 1 by T or N times 1 by T, then this whole thing is sine pi. Okay, sine pi is 0, so the output becomes 0. So if you, this is the delay line output or canceller output, you'll get this sort of response. At particular Doppler velocities, though it's a moving target, the MTI will give 0 response. So if the enemy aircraft knows your PRF by any chance, and they manage to fly at a velocity close to 1 by T also, 1 by T, 2 by T, whatever it is, the radar will not be able to detect a moving target. So that's an inherent limitation of this MTA radar. But flying very close to 1 by T and maintaining that particular velocity is quite difficult. Okay. So you'll have some response, but a bit weak response in this area. So this particular velocities, a band of velocities, the response will be weak. That's all. But still you can manage to make out that something is moving. So that is about MTA radar, moving target indicator radar. Yeah. Now for the class, do you want to ask me any questions on this? Sandita, is the concept clear?
Yes, sir. I mean, somewhat.
Yeah.
It's not very clear.
Uh, you want me to repeat it?
Yes, sir. Once.
Sure. The problem is, how do we differentiate moving and stationary targets? Right? Because the radar doesn't know. It's an incoming signal and it's just going to display it. So for that we require this moving target indicator, uh, whose basic output is nothing but the phase difference between the reference signal, that is what has been transmitted, and what is being received. So it's just detecting the phase change. Now this phase change is constant for stationary targets. Depending on the distance, right, you can make out. In fact, you can even calculate what will be the phase difference from your basic high school physics. You know what is your transmitter frequency. It's getting reflected at a distance r. And if you know how many lambdas are there in the two-way travel, you'll be able to estimate what is the phase difference between transmitted and incoming. Okay. Uh, so whether it's a stationary target or a moving target, there's going to be a phase change. Only thing is the stationary target is going to give a constant phase change, whereas the moving target is going to give a variable phase change. Now this information goes into a box called as phase detector. So as the name suggests, it's nothing but input is variable phase. So you have a variable phase and output is a voltage corresponding to phase. It's like what do you say, an FM detector. FM detector demodulator. Okay. Any change in frequency, the FM demodulator is going to give a voltage corresponding to that. Same way, this fellow is going to just tell you what is the phase change at a particular point in time. Now I record the reflected signal for one complete pulse period t for a particular pulse, store it in memory locations called as range bins. Say nothing great about range bins. Okay, so let us say it's 100 kilometers is the range of the radar. Every 1 kilometer I give a bin. So there will be 100 such bins. So I just capture the signal, dump the data into that memory location. Then for pulse, this next pulse, I'll be having another 100 data points. So respective data points, I just subtract. For moving targets, there's going to be a drastic difference, and that whenever there is a difference, I declare it as a valid target. So this process is called delay line canceller because I'm delaying it by one time period t, and then subtracting both information. There are different versions of this. I just shown you the simplest ones. Just comparing two pulses. Mathematically, the output of this subtractor, when you subtractor is again your difference, the difference between V1 minus V2 happens to be like this, having this term sin pi Fd times t. The problem with this delay line canceller is whenever Fd is n times 1 by t, the output becomes 0. So at these points, you're not going to get any output. And that's why it's also called as blind speed. So literally what it means is the radar is blind to aircraft flying at those speeds. So you have blind speeds and it speeds. Okay, it's not just one particular speed, different speeds. Then you get into this limitation of missing targets, missing and even moving targets. Is it okay now, Sadhita?
Yes, sir.
Just go through any basic books on radars, will be able to understand that.
Yeah.
Okay. Now I'll give you a small assignment for you people. We already seen this fire risk equation in which we were able to estimate what is the received power for a given transmitted power at a distance r for a particular frequency. This we already done for one-way travel. Next class, you'll have to prove that the received power in a radar, now it's a two-way travel, okay? So you're transmitting, this fellow goes here and comes back. So this received power is given by this formula, where one additional term we are going to use is something called as sigma, which is the radar cross-sectional area. It is nothing but a fictitious area which will give the same returns as if there was a rectangular plate kept vertical to the transmission. Okay. So RCS is something which is defined for every aircraft. Like stealth, it will be less than 1 meter square. Whereas if you look at airliners, it can go up to 100 meters square. Okay. So depending on the aircraft, it's going to change sigma. But anyway, it's just an area which is reflecting the power which goes and strikes it. So go through, or you yourself can derive this. Try to derive this equation. And most important thing is this received power is actually inversely proportional to the fourth r power 4. Okay, so that makes uh, it's sort of very interesting thing. So people feel that if I increase the power of the radar, my receiver signal will be very good. No, it doesn't happen so, because it's R power 4 relation. So it's increasing power really is not the solution. Okay. So anyway, that we'll discuss later. But as an assignment, just try to do this. Okay. And we'll derive it. I'll ask one of you to derive it for the benefit of the class. Okay. Okay, Sandhita. Anything else you want to ask me?
No, sir. That's it.
Okay. So just go through some standard books and try to get this relationship. Okay,
Yes, sir.
between received power and transmitted power. And these are the terms you have to look at. G is the antenna gain of the radar. Sigma is the radar cross section, what I told you. A is area of the antenna, and R is range of the target. Okay. So received power at the radar for a given target of RCS sigma. Okay, Sangeeta. So we'll meet next week.
Sir,
When is the next class? It is Wednesday. You got tomorrow also. You got a class, right?
Yeah.
Yeah, tomorrow. Yeah, tomorrow we got a class Thursday. So tomorrow you make an attempt. Okay. Let's see how you people
Okay.
do. Okay then. Thanks, Sangeeta. Bye.
sir.
Thank you, sir.